Okay, good evening. Again, second topic we need to start. Just I'm checking. So previously, what we have done, Biot-Savart law, right? And its applications. Today we will be doing Ampere circuit law. Uh, so please carefully follow what I am telling. Because this type of questions may come in the exam. On Monday, we will solve about Ampere circuit law, some applications, more applications, and some problems we will solve on Monday. But please concentrate on this video and all. Uh, and if you have any confusion, again, you can ask on Monday. So today we will start some introduction class on Ampere circuit law. So quickly we will be starting. Ampere's circuit law. What is Ampere circuit and all? So this is actually an alternative or alternate method to find the magnetic field B. Apart from the basic, we have started from Biot-Savart law. So this is an alternative method. Without doing Biot-Savart law, an alternative method to find the magnetic field, right? And already we have discussed this cross is okay. The current coming inward. We are assuming that current coming inward direction, and dot we are writing that the current in outward direction, right? So dot means outward and cross means inward. Now let us consider just basic thing we are considering. Let us consider two current, I1 and I2. One is coming inward and one is coming outward. So we will draw this thing as cross, and we'll draw this thing as dot, right? Now, how to find the magnetic field at the point P? What we have done for Biot-Savart law, that the long current carrying wire is there. We have calculated for the small differential length dl. Biot-Savart law is applicable for a small differential length. Then we are integrating to find the actual magnetic field. But for Ampere circuit law, if this is the case, so what you have to do, you have to draw a loop which cuts this point P, right? Which has to be cutting the point P. No, it will not cover the point P like that. The point P cannot be outside. Point P cannot be inside. So you have to draw a circle so that it will cut this point P. This may not be a circle. Just for understanding, I'm telling. So this point P should cuts the circle, right? And this is called Ampere's loop. This is called Ampere's loop. Please remember, this is called a loop. This is called an Ampere's loop. And the direction we are taking clockwise. We are assuming the direction is clockwise. It is rotating, right? Now there are two currents. One is flowing inward, one is flowing outward. So how to consider? We are considering that the loop is going clockwise direction, right? 1 second, I'm checking. The loop is going in clockwise direction. So which one will be positive and which one will be negative? How to do? You curl the finger. I will show the demo in the physical class because it is really difficult here. But please curl the finger, right hand finger. When the thumb is pointing in which direction, that will be your positive, right? You curl the finger. It is in a clockwise direction, right? You just curl the fingers in a clockwise direction, and the thumb is pointing in which direction. If it is inward, means outside or inside. That you need to determine. So if you curl this finger like that in the clockwise direction, so this cross will this cross is coming inward. This is inward, and we are letting this as positive. We are assuming this as positive, and this is coming outward because the thumb is not pointing, so it will be negative. So what you have to do? You have to curl the finger, right, of right hand, not left hand, right hand finger. Which direction the thumb is pointing? The thumb is pointing. In which direction the thumb is pointing? Right? If it is outside, it will be positive. If it is inside, it will be negative. It will be positive, right? Whichever direction the thumb is pointing. If it is inside, it is pointing. So inside current will be positive. So since if you curl the finger in the clockwise direction, this is pointing actually inside, right? You please do it. You will easily find that one, right? Since the thumb is pointing inside, so we have considered this as positive current. So I1 we are taking as positive, and I2 we are taking as negative. Okay. Now, what is the statement? What is the statement of Ampere's circuital law? The statement is quite simple. What we have done for Gauss law and all, right? Surface integral here it should be line integral. What I told that is q by epsilon naught. It will be mu naught into current, right? So all we are doing in a line integral. So it will be b dot dl. Both are vectors. So it will be what? Mu naught into I, but I inside, like the Gauss law. Q should be inside, right? So I should be inside the loop. It should be inside the Ampere's loop. Please remember, this I should be inside the Ampere's loop. And mu naught already, you know, this is absolute permeability that I told in the last lectures also. B and DL also, you know, this is your line integral. Please remember, this is your line integral. And what is this B dot DL? If this is the loop, if this is actually the loop, and there are two currents, right? Dot and all, I1, I2, whatever. So this is the point P. So DL will be this one. This will be DL again. Another DL will be there. Another DL will be there, like that. DL. So some small segment of the loop. This is your DL. Okay, I think it is quite clear. So which constitutes the where the small segment. This is the DL, and you are doing the line integral, right? From this point to this point, again from this point to this point, you are doing the integration. To find the actual B dot DL, it will be nothing but mu naught into I inside. I inside here, what is I inside here? It is nothing but I1 minus I2, right? Because I1 is positive, this is positive that I told, and this is negative. So I inside is nothing but I1 plus of minus of I2, right? So here your B dot DL is nothing but, you can write this as B dl cos of the angle theta is equals to I1 minus I2, right? Multiplied with mu naught. So these are some trivial things, what we can say. Some more points. You please note down, all of you. Like the same thing what we have discussed in Gauss law, because Gauss law is applicable everywhere, but it is not useful. So here also Ampere's circuital law. Here Ampere's circuital law is applicable everywhere. Please remember, in NCERT book and others, it is written that it is applicable for this conditions. It is valid for this conditions, but it is not right. So it is applicable everywhere, but it is not useful. It is not useful. So useful means you cannot use the law. So why we are using this Ampere circular law? So you have to remember some useful points, right? So it will be useful for what are the points? So point number one is this magnetic field B should be or is tangential. It should be tangential to your length of the wire, that dl vector, right? It should be tangential and non-zero. It should be non-zero. This dl should be non-zero and constant, right? So it should be tangential or non-zero or constant, like that, right? Like what I told, B dot dl. If it is tangential, means it will be what? B dl into cos of theta, right? Integration line integral. So theta is nothing but 0 degree. So it is nothing but B, and integration of dl, it will be B into L. And constant means this magnetic field B is constant everywhere. That we have done for Gauss law also. Same type of things. Please recall. Huh? This integration dl is nothing but the length of the wire. And B is constant. That's why B came outside. Right? The second one is, let's remember these points. Second one is B either should be tangential or it can be normal. Normal to the dl vector dl. So normal means B dot dl, obviously it will be what? B dl cos of 90 degree, right? It is normal. So it will be 0. Or third point is, if B vanishes. B vanishes means there is no magnetic field. The value of the magnetic field is 0. That also can be done. So if B is 0, so obviously your B dot dl will also be 0. Right? Some more points I can say that this Ampere's circular law is useful for higher symmetry. Is useful for higher symmetry. Some symmetricity should be there, like what we have done for that Gauss law. That Gaussian surface should be symmetric. Please recall, is almost similar. And another point, please remember that I inside, it should be the current within the Ampere's loop, right? Within the Ampere's loop. But your B dot dl, please recall that E dot dA in case of Gauss law, right? While finding E dot dA, what I told, electric field will be for the charges which is inside and outside the Gaussian surface. So here also the magnetic field is due to all the currents inside or outside the loop. Inside or outside the Ampere's loop. Please remember. So what I told while doing B dot dl, right? So this B should be, you should consider for inside and outside. The current should be for all. The current should be for all. But what I told, it is nothing but mu naught into I, that should be inside. It should be inside. So while applying the formula, okay. Now, what we have derived for Biot-Savart's law, that magnetic field due to the infinite straight current carrying wire. Now we will be deriving this using the Ampere circular law. How to do? Magnetic field due to infinite straight current carrying wire. How to derive or how to find the magnetic field for the infinite straight current carrying wire, right? Let us draw this wire where the both ends are infinity and minus infinity. That we have done in Biot-Savart law, right? So we have considered a small dl, some point P is there. We are making some angles and all these things. Don't do all these things for Ampere circular law. What you have to do? You have to form the Ampere's loop, like what we have done for Gauss law. Please recall what we have done for the Gauss law. You have to form the Gaussian surface, then you put the formula. So please relate the electric field, magnetic fields, all are very beautifully related, right? How you can understand that is important. So you form the Ampere's loop here. This is your Ampere's loop or Ampere circle, what you can say, or circle you can say, where the radius is r and there is the point P, and this is the radius r. When a distance is r, right, from the point P, and for Biot-Savart law, please recall this distance is r. Some dl vector will be there, everything. So the current will be flowing upward, right, like that. Now we need to form the Ampere's circle over here. Now, if you see this circle from the top view, means from the top, you just peeping, you just seeing this circle. So what you can see, right? You form this type of circle, like the radius is r, and you just form the circle. Let's say there is some straw is there, right? And you are just encircling some bangle or like that uh, with the radius is r. So if you see from the top side, what you can see? You will see a circle, right? From the top view, obviously you will see a circle where the current is flowing in the outside direction, right? Outside. Outside means dot. So current will be flowing at the outside direction. This is current I. This current is flowing outside, right? You are seeing from the top view. You will see the current is flowing outside like that. So the current is flowing up. So that's why the current is flowing outside. So I is outward, right? Now, this is your dl vector. Look here. We have this all are your dl vector. This all are your dl vector, right? So this is your dl vector. This is another dl vector like that. So many dls are there. This is your dl. Now, what is your magnetic field will work, right? And the dl vector, look here. This all the dl vectors are tangential. And the magnetic field will be tangential only. Just see, it will it will be in this direction, it will in this direction like this. This tangential. Since the current is flowing outside, you can see the magnetic field. You just curl the hand, the magnetic field will be tangential, right? Is tangential to dl. So condition number one that we that I discussed, right? This is the condition number one. This thing, the B should be either tangential or normal. So here the B is tangential. So condition number one. So B is actually tangential to dl vector. So again, B is also constant. So obviously your B dot dl will be what? B will be coming outside. This is your line integral, and it will be dl, right? You can write this as bl cos of 0 degree, right? Because theta will be 0 degree, right? Now cos 0 is 1, so it will be what? B into dl, the total length, the circumference, means it will be 2 pi into this small of r. So it will be equals to what? Mu naught into I. Now you please recall for Biot-Savart law, we will be getting this is mu naught by 2 pi r into I, or you can write mu naught by, please recall, 4 pi r into twice I. For Biot-Savart law also, we are getting this type of things, right? 2I by r, mu naught by 4 pi into 2I by r. So here also we are getting the same thing. So B is inversely proportional to 1 by r. So same results we are getting using Ampere's law. Very easily we are finding. No need to do all the integrations and all these things. We don't do all these things. Just form the Ampere's loop, right? From the top, what you can see, right? The current is flowing outside. Your dl and this magnetic field is tangential to dl. You can easily see. You just curl the hand, the magnetic field will everywhere it will be tangential, right? Since the current is flowing outside, right? Now curl the hand, right? Yeah, everywhere will be tangential. It is coming outside, coming, just curl the hand. Here also it will be coming outside. Here also it will be coming outside. Since the current is coming outside, so these are all tangential to each other. You can easily find out. So since it is tangential, so theta will be 0 degree. So B equals to integration of dl is B into 2 pi r equals to mu naught into I. Very simple. So B will be what? Mu naught by 2 pi r into I. So the same results we are getting using your Ampere's circuital law. Very interesting, right? Now another thing we will be doing today, and already I have shared some PDF of magnetics. Please go through that one. You come on Monday. Again, we will revise all these things, and we will be solving some problems and applications, right? The next question is, if the question comes like that, find the magnetic field, due to infinitely long cylind one second cylindrical wire, not the straight wire. It's like a cylindrical wire carrying current. It is carrying some current on its surface. The current is on its surface, right? And inside and outside the wire. Inside and outside the wire. And we are considering hollow cylinder. There are several applications are there: solid cylinder, hollow cylinder. So it is hollow. At the distance is given at distance r, small r, right, from its axis. How to do? And the radius of the cylinder is capital R. Radius of cylinder is given capital R. Now, how to solve this type of problem? Right? Using Ampere's circuit law. If you understood the Gauss applications and everything, it is same only. There is no difference. You form the Gaussian surface, and for radius r is smaller than r, and all these things we have discussed in Gauss applications. So here we have to do the Ampere's loop, not the Gaussian surface. We have to form the Ampere's loop, and you have to do all these things, right? So let's say we are forming a cylinder, like cylindrical, where and inside it is hollow, right? The radius is capital R, right? So inside, just inside uh, inside point we are taking P. Inside point. First case, inside point, we are taking point P, so that R is less than R. There are two conditions will be there, right? R is greater than R, R is less than R. So inside and outside, both we need to consider, right? That I do. So if R is less than R, so the radius will be less, like that, right? So that radius is small r. Another cylinder you can consider like that. I'm not drawing these things. Another cylinder inside that. Now what I told, this is your Ampere's loop, right? Like the Gaussian surface, right? For r is less than r, this is your Ampere's loop. Form the Ampere's loop. Very easy. If you understand the previous one, it is all same only, right? Form the Ampere's loop. And what you can see from the top view, what I told you, see from the top view, you will see a circle like the previous example, what we have done. You will see a circle. Now the current is flowing at this surface. Look here, the current is on its surface. So at this surface, the current is there, right? And the current is coming outside, obviously. From the top view, it will be looking the current is flowing outside. So I'm putting all as dot. I'm putting all as dot. The current will look like it will be flowing outside, and this is the where, and the radius is capital R. This radius is capital. Inside there will be this Ampere circular loop, like the Gaussian surface, right? Where the radius is small r, where the radius is smaller. So what I told, it will be B dot dl. If you don't understand, on Monday we will discuss again. But please listen one or two times, right? In the first time you cannot understand, again you just listen. I think you can easily understand. This will be mu naught into I inside, right? What I told, inside what will be the current, that is your Ampere's law and all. Mu naught into I into inside. So obviously inside there is no current. I inside is 0 here for R less than R. Let's look here. No current is flowing. No current is there inside. So if no current is there, so your B is equals to 0. No magnetic field will be there. So magnetic field will be 0 when R is less than R. There will be no magnetic field since no current is flowing inside the Ampere's loop. Now you consider the another example, right? Outside point. Outside point. Let's say Q. when R is greater than R. Now draw again this cylinder, right? Again, this cylinder you draw, this radius is capital R, right? Now your Ampere's loop will be greater than R. So this is your Ampere's loop, right? If you understood the previous Gauss applications, this is almost same. This point, let's say this is Q. This point we are taking Q, which cuts the circle, right? And this is capital small of R, right? And you can consider this another cylinder is there, right? All these things you can consider. So what you can see from the topmost view, what you can see, you will see the surface of the wire like that is circle. You will see this circle. This circle is nothing but this one. This circle is this for this one. And all the current are flowing outside. That we have discussed in the previous example also. The current is flowing outside. It will look like that. Now some interesting fact will be there. Right. Now look here. For this one, I'm drawing in green. That will be good. This I'm drawing in red. Okay. So this is in green. So your Ampere's loop will be like that, where R is greater than R. Okay. This is R. And this one is capital. This is smaller. So this is your Ampere's loop. Here all dl vector will be there. Here all dl vector will be there, and magnetic field is tangential. That we have discussed. So magnetic field everywhere is tangential, right? Everywhere is tangential. So this is dl. This is your b vector. So b dot dl. So what we can do? Integration b dot dl is nothing but b dl cos of 0 degree integration. So it will be b integration of dl, right? It is nothing but b into 2 pi into small r for the Ampere's loop, like same what we have done for Gauss application. For the Gaussian surface, your E dot dA will be same for the Gaussian surface. Here also for B dot dl, it will be same for the Ampere's loop. This will be for the Ampere's loop. I think all of you are relating what I can say. So this will be nothing but mu naught into I inside. Mu naught into I. B into 2 pi r. So finally what we are getting, B is nothing but equals to mu naught by 2 pi r into I. Or you can write mu naught by 4 pi 2I by r. Right? Now please recall, what is this? It is looking like the current is coming from the center. Right? In the previous example, this is same, right? Look here. Here the current is coming from the center, right? And we are getting mu naught into 2 pi r into I. Here also we are getting mu naught divided by 2 pi r into I. So, but what is the difference? The current is in the surface only. In the previous example, the current is in this line, infinite loop, and it is coming from the center. Look here, the current is at the center only. The current is at the center, right? But here the current is not in the center. It is at the surface. But looking at this expression, it looks like the current is at the center. What we have discussed in Gauss applications also. Please recall, it is looking like a point charge. right? Whatever we are getting for the Gaussian surface and everything, please recall that one. Same thing we are doing for this magnetism also. For a magnetic field, we are getting as if the current is coming from the center, but it is not true. And finally, if you plot the graph, I think everyone can do. If you plot the graph, what it will come. Let's say this is, one second, right? This is the cylinder where the radius is capital R, right? So up to this one is 0. Up to this one is 0. Then after that, it will be maximum, and it is decreasing because when your R is increasing, your magnetic field is decreasing because the current here it is maximum. Like the same what we have done in Gauss law also, same thing. So B is inversely proportional to 1 by R, and here your I is max at the surface. I think all of you have understood what I just recall it. This is your R. This is R equals to capital R. This is 0. This will be your R, and this is your B. Magnetic field plot. So in the next class, we will be doing some more applications. Hollow cylinder, hollow sphere, some inside, some cavity will be there, cavity resonators, circuits, and all these things are some more applications are there for Ampere circular law, and we will be solving some problems also. But please recall what we have done in Ampere circular law. It is an alternative method to do this Biot-Savart law, right? But the difference is very easily you can find out, but it has some conditions like your Gauss thing, and all are same only. B dot dl, either it should be 0, theta should be 0 degree or 90 degree. In Gauss law also we have done the same thing, right? It has some similarities, right? It should be symmetric also. Now we have determined some magnetic field due to infinitely straight current carrying wire. From there we got some expressions which is similar to that Biot-Savart law. And finally, we have considered some hollow cylinder where radius we are taking as less than the radius of the cylinder, the point of the radius, right? And it is outside point, it may be inside point. We are getting inside as 0, outside it will be the same as if the current is coming from the center, right? It has some similarity with Gauss law also, like a point charge, it will behave like that. We have already done. If you can recall and revise, you will get a similarity of the results and analysis mainly. And finally, we have plotted the graph. On Monday, we will discuss uh, the thing. So thank you, everyone. I'm stopping sharing all these things and stopping recording also.